Hi everyone, thanks for attending the session. As Kenna just mentioned, I'll be talking about solving constraint satisfaction problems using QAOA, which is based on joint recent work with my supervisor, Ashley Montanaro, between University College London and Facecraft. All right, so let's briefly state the problem we're trying to solve. First of all, we'll be talking about constraint satisfaction problems, which are relevant to many applied fields. The cliché example may be logistics. On the other hand, we'll try to solve such problems using the quantum approximate optimization algorithm, also known as QAOA. Originally, this algorithm was designed to achieve a good approximation ratio, that is to satisfy a high number of constraints on certain CSPs. In this work, though, we'll use the algorithm differently in order to find a satisfying assignment. So we want to satisfy all constraints. As it was invented in 2014, QAOA was briefly believed to outperform the best-known classical algorithms at the time for solving certain constraint satisfaction problems. Sadly, soon enough, better classical algorithms were developed that came to challenge this assumption. And since then, any advantage of QAOA over classical has remained elusive. The question that will guide this talk is therefore, can QAOA achieve an advantage for solving at least certain constraint satisfaction problems? We will address this question in the following steps. First, we will review the constraint satisfaction problem we're interested in and the QAOA way of solving it. Then we'll describe our results, which are both analytic and numerical. And finally, we'll conclude with what we learned from the talk and future perspectives for this work. Let's then start with the problem and the algorithm. In this work, we looked at a specific constraint satisfaction problem known as KSAT. KSAT is a fundamental NP-complete problem in the optimization literature, which means, sadly, that both classical and quantum algorithms are expected to take exponential time to solve it. Even a quantum computer cannot solve an NP-hard problem indeed, well, under reasonable complexity theory assumptions. A KSAT instance is characterized by three numerical quantities. First, it's a Boolean satisfiability problem on n Boolean variables denoted by x naught up to xn minus 1. Then, this problem has m constraints that we denote by sigmas. And finally, each of these constraints, sigma I, has k clauses in it. That's the k in KSAT. And we say that an instance of KSAT is satisfied if all of its clauses are. Now, how are we going to solve it, this KSAT problem, in this work? Well, we're going to try to apply the quantum approximate optimization algorithm to it, whose principle I briefly recall on this slide. The general principle of QAOA is to alternate between Hamiltonian evolution under a diagonal Hamiltonian, encoding the constraint satisfaction problem, or the optimization problem, if you prefer, and a transverse field Hamiltonian, that's this HB. And evolution times are commonly denoted by gammas and betas. So gamma for the problem Hamiltonian and beta for the transverse field Hamiltonians. Once you've performed this time evolution, you measure the state in a computational basis to obtain a candidate solution to the Boolean optimization problem. And hopefully, this measurement gives you a good enough solution. However, you don't know about that in advance, especially since QAOA is a variational quantum algorithm, meaning these evolution times beta and gamma need to be optimized. In this work, we partially mitigate this actually very relevant issue by optimizing parameters once and for all. Namely, we do optimize parameters, but we use these optimal values found at the beginning on all instances of KSAT. More specifically, how do you apply QAOA to KSAT, at least in the context of this work? Well, the cost function we choose to input in the diagonal classical Hamiltonian is the number of violated clauses, which you'd ideally want to minimize if you want all clauses to be satisfied, right? So that's our cost function, and it goes in the diagonal Hamiltonian. And we implement the ansatz using that. However, once we have prepared our variational trial state, we're not going to optimize the expected number of satisfied or violated constraints, but rather the success probability of QAOA on this problem. So we really want to optimize the probability of finding a satisfying assignment. That's in equation 7. Now, there's a major problem with equation 7 that it cannot be efficiently evaluated, right? Because computing amplitudes of even states prepared by shallow circuits like QAOA is hard, unlike computing the expected energies or the expected number of satisfied constraints. One may then consider an idea that was already explored in earlier work, which is to average over random problem instances of KSAT, and we may hope that it makes the problem easier, like the problem of computing the success probability. But to perform this averaging over random instances, one first needs a notion of random KSAT instance. Unfortunately, this concept comes ready-made in the optimization literature. That's called random KSAT. A random KSAT instance is simply an instance of KSAT which is chosen at random in the sense that each clause is drawn IID among all possible clauses on K variables. Interestingly, this random KSAT ensemble of optimization problem exhibits a satisfiability and algorithmic phase transition. So the satisfiability phase transition, illustrated on the plot, means that as you increase the ratio of clauses to variable, commonly denoted by R, you move from being satisfiable with high probability to being unsatisfiable with high probability. And this transition gets sharper and sharper as you increase the problem size. However, before even you've crossed this so-called satisfiability phase transition, you have an algorithmic phase transition, where local classical algorithms start to struggle, so to speak. Before that, they're proven to succeed in polynomial time, but after that, at least on empirical grounds, we know that they take exponential time in the instance size to solve the problem. So that's an interesting regime to explore, and that's the regime we put ourselves in this study. All right, after this brief detour through random KSAT, how can we apply that to our original problem of estimating the success probability of QAOA? Well, once again, the idea to make this calculation of the success probability easier is to average over these random instances, for which we now have a concrete definition. Okay, so assume we can compute equation 8. We still have another problem now, that it doesn't exactly answer the question anymore. Indeed, what you're ultimately interested in is about the running time of the algorithm. How long does it take to run on a single instance? And for a specific instance, sigma, this running time is indeed the inverse of the success probability as shown in equation 9, sorry. But after you've averaged over instances, this inverse average success probability merely gives you a lower bound on the running time. So you no longer have the average instance running time, you just have a lower bound on it. Still, we chose to work with this restriction mostly because, well, computing that can be done analytically, whereas for that, we're not sure at all. This leads us to our results, which again are both analytic and numerical. So let's start with the analytic part. So we have essentially proven the following proposition, which gives you a concrete procedure of estimating this average instance success probability of QAOA on KSAT for constant depth P. So it basically reads as follows. You consider KSAT, where for technical reason, unfortunately, K needs to be a power of 2. So think 2SAT, 4SAT, 8SAT, etc. And you give yourself variational angles beta, gamma, which are fixed. Then we know that for gamma sufficiently small, and this sufficiently small is independent of instance size n, the success probability of QAOA average over instances admits a scaling exponent, and this scaling exponent can be computed by finding the fixed point or critical point of a function of 4 to the power p complex variables. So first of all, one can make several remarks on this result. And the most important one is that although gamma needs to be sufficiently small, it doesn't decrease with the problem size, which is good because it's a regime where QAOA is hard to simulate classically. And second, the complexity of evaluating the scaling exponent is independent of the problem size, but it does scale exponentially with a depth p. So ultimately, you can't go very far with this algorithm Maybe p equals 10 is comfortably feasible on your personal computer, but not much further. Okay, so assuming we have this proposition at hand, what can we do with it? Well, we can basically do what we alluded to in the introductory part, namely optimizing the success probability of QAOA using this scaling exponent that we now know how to compute analytically. And this scaling exponent of the success probability, even if it's not the probability itself, we can use it as a proxy to optimize it, assuming it's good enough. Now, funny enough, we observed that doing exactly what we said led to comparable results as compared to optimizing the success probability empirically. And by that, we mean really throwing a large number of small size instances, say 100 size 12 instances, estimating probabilities fully empirically, and relying on that to train variational parameters beta, gamma. And this basically gives the same result as using our analytic procedure for estimating the probability. So this was a somehow surprising result. And this surprising result held despite the number of instances we used, 100, giving a very poor statistical estimate of the success probability. You make a 10% relative error, but you do find comparable angles as when you use the analytic procedure. All right, so let's give a brief flavor of our proof technique, namely how we prove this proposition on the exponential scaling of the probability. The main technical ingredient that it uses is that of generalized multinomial sums. So before talking about generalized multinomial sums, let's recall what a multinomial sum is. So in equations 11 and 12, you have a standard binomial sum that you can evaluate using the binomial theorem. And this generalizes to equations 13 and 14, which are multinomial sums, which you can evaluate again using a generalization of the binomial theorem, which is called the multinomial theorem. All right, should all be familiar until then. But now, what we show is that the success probability average over instances of QAOA on K-set can be cast to a sort of generalized multinomial sum. This is expressed in equation 15. So a generalized multinomial sum essentially starts like a standard one. You have these multinomial coefficients. You have these complex numbers bs raised to some powers of n. But then you have this nasty part, this exponential, which is the exponential not of a linear polynomial, but of a quadratic polynomial in the case of 2-set. So quadratic is because it's 2-set. All right. And suddenly, we can no longer estimate that, at least not to the best of our knowledge. And that's why we call it a generalized multinomial sum. At this point, to be thorough, we should mention that another work published a bit before ours proposed a different procedure to estimate a different class of generalized multinomial sums. And this was, again, in the context of QAOA applied to constraint satisfaction problems. However, these guys considered spin glass problems, whereas we consider random K-sets. And we rely on different assumptions and techniques than theirs. All right, so how does it work at a very high level, still in the random 2-set QAOA case? So we start with this generalized multinomial sum, and the problematic part indeed is the square in the exponential. So since we want the square to be linear, instead, we're going to linearize it, and we achieve that by introducing a dummy Gaussian integration variable theta. I think this trick is called the Hubbard-Stratonovich transform. And now you can perform the binomial sum or multinomial sum as you would a standard one for each value of the random Gaussian variable theta. And here, interestingly, you already have something scaling exponentially in n. You can do a bit more variable changes on that to get this integral representation where you again see clearly the exponential scaling in n inside the exponential. And what's important here is that we're integrating over a bunch of variables theta. No need to understand precisely what they are. A function which has the form of exponential of n times something dependent on theta, but independent of n. And now there is a ready-made recipe, so to speak, to estimate these kind of integrals, which is called the saddle point method. And this saddle point method gives you the existence of an exponential scaling in n, indeed, and tells you how to compute the scaling as the fixed point or critical point of some function. All right, so that was a brief overview of the proof. Now, if we apply this analytic procedure and do some numerics, what do we get out of that? Well, a first natural question is, how well do analytic predictions match up with numerics, like numerical exponents versus analytic ones? A first difficulty to address this question is that, at least for p greater than 1, we have no analytic way of estimating the success probability even after averaging over instances at finite size. Therefore, we have no choice but to estimate that using empirical averages derived from many, many instances. Concretely, what this means is that if we work with 8SAT at satisfiability threshold, which is approximately 175, we generate 10,000 instances for each instance size ranging from 12 to 20, and we evaluate QAUA on this set of instances at fixed angles and average the success probability on all of these. So this gives you empirical estimates of the average instance success probabilities, and with these parameters, they're within 1% relative error. So we're quite confident about these values. And here is the result of the comparison with the analytics. So on this plot, the dots represent the empirically derived values, and the solid lines represent an exponential fit for these values. Finally, you have the dashed lines that you can, for instance, see better on the purple curve, which are our analytically predicted exponents. So a first general observation is this exponential scaling predicted by our analytic procedure can actually be observed empirically even for very small instance sizes. Even at 12, it's okay, you already see it. And secondly, the analytically predicted exponent seemed to match quite well with the empirical ones, despite, again, the instance sizes being quite small. So that was an encouraging initial finding. And this initial finding actually motivated us to benchmark QAUA against, well, some state-of-the-art classical heuristics, because state-of-the-art heuristics can be a controversial topic. So that's what we did. And we put ourselves in the same setting, working with 8SAT at satisfiability threshold. And in this regime, we found that a specific heuristic, known as walks at LM, performed best. To do this benchmark, we used the same method as before, working with many instances and so on, except that instead of considering the average instance success probability, we considered the median running time. Because this is the metric we want to look at in the end, but we didn't look at it initially because we didn't have any analytic grasp of it. But now we've somehow got confidence that our analytic results put yourself in the infinite size limit early enough. We use this confidence we've got from the earlier numerics to just do pure numerical benchmarks. So in other words, these results are purely numerical. Okay, so that's basically on the plot what we obtained for the different heuristics. You can observe that the running time also has neat exponential scalings for both quantum and classical algorithms, which is encouraging. And in the table, you can see the exponential fits for all these heuristics. And yeah, to go to the most important point, we see that QAUA achieves better scaling exponents than classical, actually already at depth 14, but if you increase the depth even more and go to depth 60, you may even do slightly better than classical. So that's what we got from this benchmark. In summary, what did we learn from this work? Well, as a reminder of the motivation, we considered QAUA, in this case, in a different setting from the usual. Namely, we wanted to maximize the probability of finding a satisfying assignment rather than maximizing the number of satisfied constraints. In this context, we proved rigorously the existence of an exponential scaling of the success probability, which held at least for a restricted range of variational parameters. And we validated this theoretical finding using numerical benchmarks. The most important lesson from this benchmark is that the so-called infinite size limit is attained for actually pretty small instances. Even for 8SAT, which is quite a dense kind of problem, you're done at size 12. Finally, we learned from this benchmark that QAOA seem to outperform Grover's algorithm at constant depth, while Grover's require exponential depth, although there are some caveats to that because there's a subtle interplay between empirical and analytic analysis here. And finally, one may be motivated to believe from these findings that QAOA has a scaling advantage over classical algorithms we tried for this constraint satisfaction problem of random k-sets. Thanks for your attention.
Thank you for the really nice talk. Are there any questions?
How did you estimate the runtime for QAOA?
Yeah, so the running time was estimated using the same method as the success probabilities, namely throwing tens of thousands of random instances for each size and averaging. And once again, we get a 1% relative error on these for each point.
Okay, and any of these classical algorithms, are any of these in like the sum of squares formalism, or are they all other kind of heuristics?
Good point. I think most of them are branch and bound variety kind of algorithms. That's the case of MapleSat. But WalkSat LM is actually just a slightly more sophisticated variant of WalkSat, which is a very basic algorithm for SAT.
Thanks.
I have a similar question. So what is the y-axis showing? Like, is it simulation time or?
Yeah, so the y-axis is showing the median running time, which...
Measured how?
Yeah, that's a very good question. So that would be measured differently depending on the solvers. So for instance, for branch and bound solvers, you'd have to combine the number of conflicts you find, the number of branching steps, this kind of stuff.
So you count steps. It's not like runtime in seconds or anything.
Oh, no, because that wouldn't be comparable between quantum and classical because of different clock speeds and so on. Yeah, there's no cheating on this side. And actually, if you think a bit about it, the fact that we only found a mild speed up of QAOA over classical means that it's not clear yet whether with concrete clock speeds on quantum processor, you'll have an advantage. Yeah.
Okay, thank you.
Actually, just quickly, I have a related question. So for the theoretical part, you talked about how the runtime that you find is actually a lower bound on the average case runtime?
Indeed.
And so in your numerical simulations, is it still a lower bound or?
Yeah, it's still a lower bound. I think here we haven't put the plot with both the running times and inverse success probabilities, but you clearly don't see the same scaling exponent, although they're decently closer. It's not going to be, they're not going to be the double of one another. Yeah.
Do your simulations of QA include an error budget, or do they just implicitly assume fault-tolerant computing?
We would say for this constraint satisfaction problem, we assume fault-tolerant quantum computing because it's a dense problem with many clauses. With many clauses per variable.
Thank you.
There are no other questions. We have a break until 11:30, so see you back then.